One of the big reasons why we've been talking about mass balance and flow and flux is because we have significant sources of pollutants that flow into water and then flow out of water, not just pollutants, well, a variety of different pollutants that flow into water. So if we think about the types of pollutants that are going to be in water and where they come from, we have really two main sources, and these are industrial sources, and I'm going to group mining in here. And these are usually things like heavy metals, like lead, mercury, cadmium. These are also things like caustic materials. So you can often have strong acids or strong bases. We've already kind of talked about some acids and bases and how that chemistry affects water, but mainly just from a pH standpoint. And then we also can have some solvents. So industrial mining wastes can really run the gamut from organic solvents to strong acids and bases, heavy metals, and almost everything else in between. And of course, in the past, there have been a certain number of radioactive industrial byproducts as well. So I guess we can put radioactive ones in here already, or as well. Although we have talked a bit about radioactive materials, and we don't really have time for a whole lot of discussion more about those ones. So industrial and mining is a big area of pollution. And then the other really big one is agriculture. And you may be asking me, well, what about, consumers and commercial stuff? And yeah, we do produce some waste, but compared with the amount of waste produced by agriculture and industry, our waste stream is relatively under control. And there are usually really strict guidelines for communities for how to deal with public waste. So, for example, at least in the Pacific Northwest, you have to sign up, if you're in a city, you have to sign up for some kind of garbage disposal. So somebody's picking it up, so you can't just dump it in a big pile in your yard. You are either going to be hooked up to a sewer system or a septic tank system, and so those wastes are handled in a processing plant, and there are lots of regulations that have to go into that. And although there are regulations that go in for industrial and agriculture as well, the EPA has only been in existence since 1970. And so there was a lot of stuff that happened before that didn't get tracked at all. And there's even been a lot of dismantling of EPA clean water and clean air guidelines in the last 4 years that endanger our ability to make sure that we have clean water to drink and clean air to breathe and clean soil to interact with and stuff. So as far as agriculture comes in, these are going to come into multiple categories. So we're going to have fertilizers that are directly applied. We're going to have pesticides, and this covers insecticides as well as plants, like weeds and fungus. All of these fit under the category of pesticides. And then you also have animal waste, which is not insignificant. So these are our two big categories. I'm going to save the industrial and mining conversation for a little bit later. I'm going to focus just in this video on the pesticides because that's enough of a conversation just in and of itself. All right, so pesticides, we've already talked a little bit about DDT. And DDT is one of our most famous examples, but we actually have a pretty wide set of examples of different pesticides. Our book has a nice summary of a bunch of different kinds of pesticide types as well as their chemical structures. Some of them are very specific chemical structures, and some of them are, sort of just a class of compounds. And I'm not going to spend a lot of time talking about these different ones because not everybody in this class has the same background in terms of organic chemistry. But if you're interested and you have background in organic chemistry, take a look and look at some of the different classifications. So each of the different categories is classified by a functional group. So for example, there are some diphenylmethane, gosh, I can't even talk today. There are some that are in a cyclohexane group. There are some that are chlorinated, some that are not. So you can take a look and get a general sense. I'm going to switch you over to another image right here. So this is from a journal article that talks about different classes of pesticides. This one is looking specifically at insecticides. And for the synthetic ones, our book is focusing mostly on these organic ones. And this particular article only lists 4 different categories of organic ones. And they list them as sort of big categories. But you can see that we also have some inorganic ones which get mentioned as well. And then you have some ones that are plant-based, or in other words, they are appearing in nature. And that is really the difference here between natural and synthetic. Something that is natural appears in nature. Something that is synthetic is made in a chemical laboratory. We've already talked about why DDT was discontinued. And DDT is one of a number of organic pollutants that has been named in the Stockholm Convention on Persistent Organic Pollutants, which is an international treaty that the signers agree to stop using these different organic compounds. And all of the ones that are named in the treaty, and there's, I don't know, a dozen or so, are ones that cause human harm and harm in the environment and persist in nature for a significant amount of time. And the Stockholm Convention is not the only environmental treaty that's out there. There's actually quite a few. Unfortunately, there's not as many that we, the United States, have signed and have agreed to obey. And this, I think, is something that we need to change in the future. So coming back to pollutants in general, these pesticides, specifically, they get categorized as well as by type, but they get categorized by generation. And the generation is indicated by how they act or how they are made to work. So the generation 0 is the most basic kind of pesticide, which is a physical one. So this is a physical intervention. So this would be something like using a barrier to prevent pill bugs from coming up and eating your strawberries. So this would be an example of using things like picking off cucumber beetles by hand or weeding. These would all be physical interventions, using nets to prevent birds from coming in and eating blueberries. So all of these are physical interventions. And these are perfectly effective. They just tend to be more work, more labor intensive, and not always 100% effective depending on how persistent your pests are. So generation 1 was a series of inorganic compounds that were super toxic. And they got discontinued quite quickly. There were 2 in particular that our book mentions. One of them was called Paris green, which was actually a pigment as well. It was a copper and arsenic compound, and it was really pretty bad. It's interesting because it's not the only green pigment that was toxic. There was another one called, I think, Scheele's green, and people used it to dye clothing and stuff, and people would get poisoned just from wearing the clothing that had the dye on it. And the same thing was true for Paris green. I mean, this seems like a bad business model, right? Another one would be lead arsenate. You can just hear from the name that maybe this is maybe not the best for you. It's got a lot of lead, it's got a lot of arsenic in it. Neither one of these were particularly good. So they were very toxic. And they didn't just kill the pests, they also killed people. And they got discontinued. Thank goodness. So in generation 2, we have kind of two groups. We have a 2A and a 2B. And the 2A ones are organic compounds like DDT. You can sort of think of them as first generation organic compounds. They were not hugely reactive, so they persisted in the environment. They were not super toxic to mammals, although still carcinogenic. But they caused other environmental problems. So, as a response to the problems of the 2A group, there was a shift to using more organic compounds that were kind of alluded to this earlier, that were less persistent, but actually more toxic to mammals. And then finally, we also have a generation 3. And these generation 3, I think the 2A, the 2B, and the 3 are all more focused on insecticides than they are on the other compounds, although this isn't 100% true. But these were chemicals that were tailored to be like hormones. And these are mostly like insect pheromones, for example. And these ones are probably designed to also be toxic rather than just, say, drive them away. So there's a lot of really interesting insecticides and herbicides and fungicides. I don't know. I consider them to be a little bit more passive because plants don't move around and mushrooms don't move around. I mean, they send spores and pollen and stuff. But insects are a lot more active, and they are animals. And so when we think about insecticides, you know, there's definitely some arguments for using insecticides. Insecticides. I mean, look at, for example, at the locust swarms that have been going on in various places in the world this summer. It's possible that there are some other causes of these swarms and that they could be controlled in other ways that were more preventative. But certainly for the people who were on the ground, who were having their crops eaten, you know, the use of some kind of a poison is a fast and effective kind of thing. So pros, they certainly control out of control insect populations. And they also really do help control insects that spread disease, mostly mosquitoes, but not just. Because there's some pretty nasty diseases, you know, malaria, dengue, I'm not sure I know how to spell that. I think I've got it right. Zika is a new one, cholera. So there's definitely reasons why you'd want to be able to control insects as needed. But there are also some problems for taking this approach. That many pesticides, many insecticides, they are indiscriminate. So they kill beneficials as well. And there's a lot of beneficial insects. Certainly we are all kind of familiar with pollinators like bees and butterflies. But we also have a lot of beneficial wasps that help keep other insects under control. Ladybugs are another one of those, dragonflies. And, these beneficials provide food for birds and for fish. In fact, not just the beneficials, but all the insects provide food for birds and fish. And so you risk messing up the food chain if you take out one of the lower rungs of the food chain. Because insects, they're a fairly fundamental group on the food chain, and so they're going to have an echoing effect all the way up the food chain that could be really, really problematic. I mean, certainly we can even look at our pollinators first and say, well, if we aren't, we're going to feel that if we're not pollinating all of those food crops that we rely on to eat, then we're going to suffer from that as well, not just birds and insect or lizards and things like that, and snakes. So you've probably heard about some honeybee colony collapses, which may or may not be tied to the use of insecticides and herbicides. The science is a little bit unclear on it. And we are seeing some pretty significant disruption to insect populations. That doesn't mean that they are totally gone, but I'm going to post an article up that looks at, it's a newspaper article, not a scientific article, that looks at some insect populations in Washington state and how they're seeing some significant disruption, areas where insects are not present, or a particular type of insect is not present that's usually there, and it's in other places in the state, and places where insects are, really, like some of them are doing super well and other ones are totally absent. So there's definitely a lot of sort of strange stuff going on. So I'm going to try and, touch on a couple of other important chemistry side pieces here as we think about pesticides. And we think about the chemistry and the implications. Of course, there's chemistry in making synthetic pesticides, but we're not going to talk about those ones today. That's going to be mostly an organic chemistry kind of talk. But instead, what we want to talk about is focusing on what we need to be aware of in our environment for implications of these pesticides. So, our questions that we need to know is, what do they do right away? So when you apply that pesticide, whatever kind it is, what is it going to do right away when it hits your field, for example, or when it hits? It depends, I guess, on what kind of pesticide you're using. What is the physical activity of it, and what is the chemical activity of it, and perhaps what is it going to do? Am I going to need to worry about a whole bunch of dust being on my crops? Am I going to have to worry about having to clean up a bunch of dried up plant waste, or am I going to be able to compost it? So this is one of our first questions. Our next question is, where do they go? And what I mean by this is, are they volatile? Are they going to go into the air? Are they water soluble? Are they going to go into our streams and rivers and lakes? And then eventually to the ocean? Are they fat soluble? So are they going to accumulate in tissues? Either in the tissues of fish or in birds or people or whatever. Are they going to bind the soil? So are they going to stay in my dirt? Are they going to potentially kill all the microbes in my dirt? You know, there's a lot of questions that we have and that we need to know about if we're going to use these pesticides. In addition, some pesticides, it's not so much the first application that is as toxic, but some of the byproducts of them breaking down are also toxic. So what do they break down into? And how harmful are these breakdown products? And then how fast do they break down? So we're starting to have some of the tools to deal with questions like number 4 when we do the math. And also question 2, you know, when we're looking at things that are water soluble and asking how much accumulates in the water, because that's part and parcel of this question number 2. Where are these pesticides going and where are they going to build up in our environment? So when we think about some of these other pieces, this also, you know, in here, in 2 especially, this requires us to know about chemistry as well, because all of these questions are answered by our understanding of chemistry. So things that are volatile are usually small molecules, often organic or made out of non-metal elements. Non-metal. And so if we study the chemical structures, we can predict whether or not these are going to be volatile. If we think about water solubility, we're going to look at what components are in it, and we're going to need to know our solubility rules. And if we're thinking about fat soluble, these are often organic. And some of our organic compounds are also water soluble, so we need to be able to look at the functional groups and predict whether or not those organic molecules, like a heavily chlorinated molecule, is probably also going to be water soluble, because those chlorine groups will help bring it into solution. So one of the questions that we need to know if we're thinking about these fat-soluble molecules is that we have to realize that if these molecules are going to be in agricultural products, you know, if they're going to be applied to grains that are being fed to animals, for example, then we might have to pay attention to them building up in meat or milk or even on the produce that we're eating. And so it's really important for us to pay attention to what some of the implications are of the chemical compounds that we're putting on the land in any way. So I'm going to stop this video here, and we're going to talk about some of the other pollutants in another video. But hopefully this is giving you a good idea of some of this kind of introduction for how we think about what kinds of pollutants are going into our systems.